Okay, thank you for the invitation and also to give me the and it's a very classical way of introducing myself. The pleasure of introducing some of the work we've been doing, and it's actually it's kind of a personal journey. I'm a geneticist for those that do not know me. Working on fundamental science for a long time, and then I moved, let's say 15 years ago, to something more applied, and in my case, a little bit more meaningful in terms of research. And what I'm going to try to show you is some success and failures we've been having with diversifying crops and trying to breed new crops to face some of the most important challenges that will be the agroecological transition. So let's move first to the end, actually. And probably that's something that's, when I started to work on that, that's something that was really, really weird for me. I've been taught breeding for specific traits, such as yield, such as tolerance to pests, etc. But dealing with agroecology is something that was very difficult to handle at first. First, because that's a definition from the FAO. It's a holistic integrating approach. It seamlessly applies that we all remember ecological principles, but we sometimes forget the last part of the sentence with the social concepts. And that you will see it's quite important. That's probably one of the most difficult things I had to face, actually. So it goes through the classical things like optimizing interaction between plants, animal, humans, and their environment, address the need of social fair food systems. It's actually science, but it's not only science. Also, we tend to forget about that. It's also a set of practices and a social movement. And what's very important is transdisciplinary field. And that's probably why we have such difficulty. And I think Annabelle just pointed out that when we are leading one of the 4 flagship, and you've noticed that's only the one that's has not started yet. And we can come back to that later on, but there are some explanation. And one of these explanations is transdisciplinary. Okay, you've seen that, you know that we usually will focus on the 13 principles, but do not forget there are 10 elements, and these elements actually have been built by a multi-stakeholder process, and not only experts. What's interesting, these 2 things are they're connected, and if you try to focus on what breeding can address, the circles, the plain circles are the classical ones, you know, working on animal health, soil health, recycling, input reduction, etc. That's kind of things are pretty easy to deal with breeding. However, the one with the dashed circles, that's some of the topics that we can address, but it's not super easy. And it's a little bit off what we usually do. So, for instance, participation, social values, co-creation of knowledge, synergy, etc. And I will come back to that later. Okay, so now if we want to translate all these principles in breeding, we can have plenty of different ways of doing it, but developing low input cropping system is kind of an obvious way to go. Adapt to the local dimension and diversity of practices. That's something we can kind of forget usually. We try to find the magic bullet of the variety, the crop species that will fit all conditions at once. But maybe we should step back and think maybe varieties that will be more adapted to specific conditions. Increasing inter-species diversity. That's something also quite challenging. And provide ecosystem services, including non-market and support services. That's also pretty challenging. Monitoring yield, that's pretty easy. Monitoring other services like soil health, that's pretty complicated. Optimize plant-plant and plant-soil interactions, that's not super easy as well. Introduction of service plans, diversify crop rotation, simplify the cropping systems. So the idea was, can we try to find a way to move from these very abstract concepts to a more practical system? So moving to a proof of concept. So the idea was to have a couple of ideas, like choose a plant species that promote crop diversification. So the basic idea is that let's not work on the cash crops. let's work on other crops that would improve diversification of our cropping systems first. Second, try to evaluate this crop into alternative cropping systems. And what I mean alternative is maybe moving away from monoculture. Since we know all the drawbacks that could come with the monoculture. Third principle, try to evaluate the provided service in the field. I should have underlined in the field, because studying agroecology in the glass house is meaningless. So the idea is to actually work in the field, and as you will see, that's actually one of the issues we have. Identify limitations and bottlenecks, select potential traits able to improve the cropping system, and identify or create the genetic resources. So when you go from that to more applied things and practical things, I decided a couple of years ago to move into a species from the Brassicaceae species I will introduce just in a while, and try to develop not monoculture but inter or mixed croppings, having something that we cultivated in France, work on the limitations associated with these new cropping systems, and in particular the relationship with the biotic stress and the cell cycle, the cultural cycle. Try to find new traits, and I will discuss one of them, the flowering time, and so identify and create genetic resources to help coping with these challenges, working with natural accessions like land races, recombinant lines, and obviously DT. So what I will show you today is, people who know me will know that I will talk about my favorite plant, which is Camelina sativa. And so I will just give you a few slides to introduce you to the crop, the biology of the crop, and then the cropping systems, and the traits that we could develop to better yield this alternative crop in the context of the agroecology. Okay, so it's an old, so old actually compared to wheat, etc., but it's been recorded to be used or cultivated since the Bronze Age. It's a low input, crop tolerant, drought, heat, and cold. And actually, there are some agronomical book from the 19th century already mentioning all the potential of this crop. It completely disappeared with the cultivation in the 20th century of rapeseed and sunflower, at least in Europe, Western Europe. It's still cultivated in Eastern Europe, especially in the Baltic countries, Belarus, Ukraine, and Russia. It has winter and spring cultivars, especially in the East Europe. You will have mostly winter cultivars, very resistant to cold. And in Western Europe, you will have more spring cultivars. It's a fairly short cycle, 100 days. The yield, well, it's quite optimistic actually. It's more rather 0.7, 0.8 ton hectare if you have no input. Of course, if you apply nitrogen, etc., it's a Brassicaceae. So you will increase the yield. But let's say if you have a low input conditions, it will be roughly around 0.7, 0.8 ton hectare, which is pretty low. However, it's interesting because this oilseed crop is pretty rich in omega-3. Not as rich as flaxseed, which is the richest, but the second richest in the crops cultivated in Europe. What is very interesting compared to flax seeds, actually, so it's pretty rich in tocopherol. So it's actually an oil that you can keep on the shelf for weeks and months, actually. While flaxseed, no way you can do that. It will be oxidized. Okay, you probably use Camelina already. You can find, you have an organic field sector, which is quite dynamic. You can find it in some shops. You probably use in cosmetics because as soon as you have omega-3, you probably have Camelina oil. But actually what brings Camelina back into the market right now is the biofuel, the need for greening kerosene. We can discuss about that, but everybody knows that's not sustainable, but it's actually something that could bring the Camelina in the market. If you just we made some calculation with students. If you just want to provide Air France kerosene from camelina oil, you probably would need 80% of the French surface. Just to give you an idea. Why some people are looking for alternative oil production, mostly because the idea for Europe as actually forced to use oil coming from different sources as a food and feed. And one way to do it is actually to cultivate camelina as a catch crop or summer sowing. So it's a cover crop. So the interest in that is that it's a time of the year where you can have bare land. Instead of having bare land, you just have a cover cropping systems. The interest of camelina is that you have a cover cropping system and the farmer can harvest something. And if you harvest something, you can value, it has a value for that. So camelina can be grown as a main crop. It's not super interesting unless you're very interested with the oils. Classically, the oil for food that you see in the organic farming systems. As a summer sowing, that's pretty interesting, especially after winter peas and winter barley. And in France, as you see, you have a small acreage that's been cultivated. So the idea is actually to have a sowing at the end of June, basically early July. Or you can have a relay or mixed cropping. Here you have two examples in the US and in France, either with lentils or with soybean. Okay, so let's move into the plant itself now. Camelina is a great crop. It does what initially thought as a major drawback. It's an hexaploid species. So meaning it has free subgenomes. Not only does free subgenomes, but these free subgenomes are super closely related. I mean, if you look for one gene from your favorite Arabidopsis plant, you will find 3 genes that are almost identical. And not only they're identical, but they are co-expressed almost at the same level. So it's actually very strange that this plant, there are not subfunctionalization of these homeolog genes in this plant. So these 3 subgenomes have stayed like that for a long time, and nobody knows why. So it has 20 chromosomes, almost 90,000 genes. As I said, 3 closely related subgenomes. So you can really see, for instance, the chromosome 20, which has no duplication of the other chromosomes. What is very interesting, it made my life super easy. It's very, very closely related to Arabidopsis. Basically, if you have your favorite Arabidopsis gene, you will find the 3 homeologs in camelina. No problem at all. And most of the regulatory innate portion of Arabidopsis is conserved in camelina. So that's very convenient. The second reason why camelina is very attractive is because it's super easy to transform. You just do flower dipping the same way as you do for Arabidopsis. So however, for genetics, that could be a nightmare, because if you have 3 very closely related subgenomes, you have high redundancy. So if you want to get your favorite knockout mutants, you will need triple mutant. That's a genetician nightmare. However, we have some collection genetic diversity for this crop. I have to just remind you that there is no wild Camelina sativa. There are some wild relatives. It's called Camelina microcarpa, but there is no wild Camelina sativa. There was one report in Turkey, in Anatolia, but many people think it's just a seed just fell off the truck and probably not the real origin of the crop, even though probably the origin of the crop is in this area of the world. So now we have a pretty good idea of the genetic diversity of this species. It's actually pretty low. So we have basically all the species are coming from Europe and Eastern Europe, but the actual genetic diversity is actually pretty low. Just for the expert, the polymorphic information content, the peak content is 0.1, which is pretty low. However, if you look at I should not say however, on top of that, if you look at these 220 accessions and color-coded according to 4 arbitrary ancestors, that gathers most of the genetic diversity of the species. Basically, you can see that there is not much genetic diversity. For one very obvious reason, it's an autogamous plant, and it's probably self-propagated in local area without much exchanges of genetic material. So the genetic diversity is originally pretty poor, and even it's not well distributed across all the land races that's been collected so far. So we are facing with two challenges here: rather low genetic diversity and an exaploidy content. That makes genetics not very easy. However, you can still do it. So I just took some examples. You can do some GWAS. And it's just took this nice paper in 2021, where they look for oil content variation. You could see with this Manhattan plot that you can pick up some genes, and clearly lipase, which is kind of obvious. Some polymorphism could be associated with change in the oil content, but as you can see from the graph, it's not super exciting. You do get some variation, but very low actually. So you don't have very strong genetic leverage. It's even worse, I would say, if you look at the oil profile. So here is the oil profile of camelina, and that's the oleic acid from the same one as olive oil. And just focus on this one. It's around 16%. But basically, the outliers, I mean, the best one you will get is around 19%. There is kind of a glass ceiling that would just, you will not cross, and all across all the genetic diversity that is known for this plant. So I think that the oleic content is a very interesting test case, because it shows you what you can do with this crop. The first thing you have to understand what's going on with this olive oil. Basically, oleic acid is synthesized from stearic acid with a desaturation, and then desaturated twice more with two desaturases, fat-2 and fat-3, that provides you with linoleic, and it's an omega-6 fatty acid, and linolenic, which is omega-3 fatty acid. So the first thing is, you can increase genetic diversity by EMS mutagenesis. That's been done by the colleagues in Canada, and it's done a pretty heavy mutagenesis, actually. And they screen for 3,000 M2 plants to identify mutants that will increase from 17%, as I said, 16, 17% the oleic acid. And they got actually a mutant with 27%. So we moved up with oleic acid. That was very good. However, only one homeolog has been mutated. Remember, there are two others that could, and they could not recover plants that with higher oleic acid. Second strategy is moving into transgenesis and doing either antisense or RNAi. And in that case, in these two studies, they move up to 50% oleic acid, because at that time they could actually inactivate the free homeologs, but they could not get complete inactivation of the free copies. Finally, the last strategy was to actually use editing. So in that case, it's been the work we've been doing. The nice thing about editing is that you can edit the free homologs, and you have gene dosage effect. So by the quality of the allele combined by the quantity of the homolog mutated, you have a range of oleic acid content in your population. So it's very nice, because you really increase the diversity so that you can basically pick up the oleic acid content you want. So it turned out that this exaploidy is now an advantage, because now you can change, as I said, the alleles and the number of copies mutated. And you could recover that time more than 63% oleic acid in the seed, which is almost the flaxseed content. So we were very excited about that, since we were able to get a complete knockout of the saturates. That was super nice. So the idea is, since there is a real need for diversification of oleic source in terms of complex system, we thought, wow, we have the magic bullet. We have the perfect plant to grow intercropping species to provide an added source of oleic acid. Well, that's where we started to fix problems, let's say that way. At that time, it was in 2017, editing plants didn't have any specific regulatory process or regulatory, there was no regulation basically for these plants. So we decided to actually do the field trials of these plants in UK. In UK, there are the advantages in Rotherham State that they have a specific field trial system for GMO. And I think we were very wise to have done that, because in the middle of this trial, the European court decided that edited plants were GMOs. If not, we'd have to destroy these plants at the time. But we were safe because that was in the case, specifically, they were tested in this context of GMO. Well, I think that's one picture speaks up for all everything. Here is a 60% oleic. Here's a wild type. Here's the 30% oleic. The magic bullet just doesn't work. So obviously, this oleic plant was absolutely not fit for agronomic purposes. However, we could check, and actually we move even up to 50%, where it's still compatible, at least with the British weather. But 60%, no way. And for an obvious reason is that for biology, we know that polyunsaturated fatty acids are very important for temperature tolerance. And obviously, if you reduce polyunsaturated fatty acids, you will decrease tolerance to cold. And unfortunately, UK.
It was not obvious in the greenhouse.
It was actually, we had a not so strong phenotype. Yeah, it was slightly smaller, but actually, I will come back to that. I don't know if you can see it, but it's the plant has a specific architecture. It's the apical dominance is reduced and small, bushier. And actually, we were very excited about that. You will see just in a minute, because that was a trait we were very interested in, is having a plant that would occupy the space on the ground and fight off weeds. It's slightly more effective. So we were actually ready to lose a little bit more in terms of yield, but we were not expecting having such very strong effect. So clearly we gave up on oleic acid, because obviously we could not actually have this plant ready for the field, but also because we thought at the time that they were not addressing what I've just presented at the beginning, the agroecological transition, and apart from the fact that it would increase diversification, it would provide new source of oleic acid oil. So we discussed with colleagues at agroecological, especially, and in RAE, especially Marie-Hélène Geoffroy, Chantal Lois, and at that time, her PhD student, Margot Leclerc, who is now a scientist at agroecological in RAE. And they, at the time, that did very nice work, working with farmers, try to identify what will be bottlenecks and in growing camelina as a cover crop, summer cover crop. And what came out from the study is that there are two basic bottlenecks. The first one, we were discussing that, is weeds. If you grow a crop in summer, the problem you are really facing is weeds, already the weeds. And the second was actually they could not get the plant mature at the end of the cycle, especially end of September, early October, because it's getting humid, temperature drops, and it's not the ideal conditions for seed maturation. So what they really wanted is to have early flowering land races and to have plants that would be better adapted to fight off weeds, actually. So the land races, we looked at it. I think a slide, yeah, no, just to show you one thing before moving into genetics. We've been also growing camelina as a crop. I see that Adrienne is in the audience, so she knows what I'm speaking about. And at first we said, well, maybe before moving into genetics, can we actually improve the way we grow the plant? And so we tested as part of the Untwist European project. We tested we can actually make some changes. We tested first in the seeding system. We tested broadcast versus row seeding, that's a classical seeding. This one could be advantageous to have a better surface occupation of the plants, and so to fight off weeds. The second was important, was to accelerate maturity by doing cutting and swathing on the French. So cutting and swathing, you cut and you let the plant dry on the ground. That was effective, actually. You could really speed up the maturity. It's actually technically not super easy for farmers to do it, because you have to harvest something which is lying on the ground. You have to cut it so that it doesn't actually get too wet, etc. But you can still do it. However, it's not enough. These two actually crop management is not enough. For instance, in 2022, you probably all remember, at least the one in France, that summer was pretty hot. Very hot, actually. We had 45 degrees in Versailles, and it delayed germination. Camelina is not dead, but the germination was delayed because there was no water on the surface of the land. And since germination was delayed, flowering was delayed, maturation was delayed. It basically, at early October, we were facing a high rain, actually, and the plant just rot and was moldy, and we lost the harvest. The only one we saved was actually the one that was cutting and swathing and row seeding. That these two conditions together was the only one we could save, but that was pretty difficult. So it means that even with new cropping strategies, well, it's not enough. We need short cycle varieties that would actually be better fitted for summer cropping. So what do we have in hand? We actually have land races, and we can find, Céline is the French reference. It's been selected and certified a long time, 15 years ago, I think. So it's kind of our reference, and we can get 3 to 4 days precautions. We can have actually even 10 days or 15 days, but these plants clearly are not crops anymore. They are so early that they're almost no yield, and there are some very strange developmental effects as well. So we also tested recombinant lines. We actually selected lines in the field, and we got 4 or 5 days compared to the reference. So it's pretty much the same as the land races. So we thought, could we actually try to go further with editing, so to provide a little bit more precocity, and also to have added traits and that would fit with the summer cropping. So just to scare you a little bit, that's an old regulatory network for flowering in Arabidopsis. Actually, there's a very nice paper from the Canadian colleagues very recently demonstrating that this network is almost identical in Camelina. And there are plenty of genes, especially LHP1, SVP, ELF, the TFL, that actually repress our flowering, meaning that if you mutate these genes, potentially you will accelerate flowering. 5 minutes? Okay. And we did that. And we did multiplex editing of these 15 gene repressor flowering, selected over several generations. And what was interesting is that we could get early flowering, but also we could get determinate growth. That's a very interesting trait, because you basically have a terminal flower that stops flowering, that help synchronize the culture and avoid reflowering in September and October. That was a very interesting trait. And the other trait is the one we discussed with oleic acid, is the bushy phenotype. So we could combine these different lines with the different traits. So darker and stronger the phenotype is. One white, you have no phenotype. And see, well, you don't have ideal line, but you can have lines that combine these different types that would be worth testing. And what's interesting is that these lines, I just want to make a comment with that, is that we did test these lines in a glass house. They under control of stressful conditions, because when I mean stressful is drought, severe drought actually. There's 5% water, residual water in the pot that Arabidopsis is dead in these conditions. So that these conditions. So you can see that flowering is actually more precocious in stress plants. Everybody knows that. It's a little bit the case for the flowering, but it doesn't change much the earliness of these plants. What's interesting is, however, that the branched plants that are here are completely unbranched in stress. So that's an expected result, but that's actually could be a problem in the field. So, and because that's what we were expecting, and we were expecting that even though it was stressful conditions. So this decrease in bushiness, that's something that we need to evaluate. I will move that later. So, and I will be done. What's next? The next step is evaluate these plants in the field, because it might be, again, not the magical bullet we're looking for, but at least to see whether it improves something or not. And the only way is to do it in the field. And I hope that one day we'll be able to do it in France. The second is that flowering, that was the easy trait, but there are other traits that are important, especially the one with allelopathy, the relationship with the microbiome, etc. That are not very easy. There are some very good teams, especially at GBB, working on that. But you know, that's traits that might be worth considering. It will not be super easy. What is very important, I think, is that we discuss with farmers, because by discussing with them, I realized that sometimes what I thought was obvious is actually not obvious in the real conditions. And that's something we are not super at ease doing that. And I think that's what we have to do now. Should we go further than just asking for advice? We should go now, like people in ecology are doing it for a long time, is to do co-conception of research programs with them. That's not easy, because that's not the way we've been trained. And that's changed, I mean, the way we do research. But I think that's very important in the future. And finally, and I won't comment on that, but I think the accessibility and the fairness of using these lines are very important. And I really hope that we will move into regulatory of these plans that will consider that point. And I don't know, we will see. And I think I will end up here. And just thank you, my colleagues. Very important. In bold, especially Fabian Noguet and Anushka, and Yannick Belek, Lionel Gissot, and Mark Difford, that describe most of the plants you've been seeing, and all the partners we've been involved, including the people from agronomy, ecosys, and all the Centuries project, as well as my colleague and a longtime friend, Jonathan Mayfield. Thank you for your attention.